All right, so these are the difference in means problems. Again, looking for significance, okay? Keep that 5% in mind, 0.05, right? So 22 students were randomly split into equally sized groups. Each member of the first group, group 1, used online math homework, and each member of the second group, group 2, used paper math homework. Ooh, interesting topic right now in terms of the COVID type of teaching we do. Both groups were given the same test at the end of the year, and the test results were shown. What inference can be made about the results? So again, we're looking here to see, if one group has a significant difference than the other, right? So if we take a look, let's do group 1 minus group 2. So we would say we're going to do x bar 1 minus x bar 2. That's sample mean 1 minus sample mean 2. These are each sample means. So 65.8 minus 80, sorry, that's terrible, 80.9. And when we do that, we're going to get a mean score of 65.8 minus 80.9, negative 15.1. So we are trying to see how often this difference occurs by chance alone. And that's where we come down here to what's called our histogram. All right, so this is a histogram. It's not a dot plot. Each bar represents a value. And again, the number to the left is included in the bar. Okay, so like for instance, this bar, this number right here is 10. So 10 is included. A difference of 10 is in that bar. So we're looking for a difference of negative 15.1. So here is negative 12. Here's negative 14. Negative 15.1 is in this bar. And again, we're going to go one way or the other. So we're going to go to the left or less. Okay. So we're looking at these two bars. Now you have to come over here to the frequency to get how much each bar is worth, right? So this is 0 to 5. So this middle one is 2.5. So because this one stops short, this bar represents 2 samples simulated out of the 250, and this represents a 1. So that's 3. 3 total simulated differences out of the 250 simulations came out with a negative 15.1 or less. 3 divided by 250 is a probability of 0.012, which is definitely less than 0.05, which means this difference is significant, right? So if we look here, group 1 received the online math homework. They scored very much lower than the paper one. So again, this example is showing that paper is actually better for people when they have to take tests. Not good for COVID teaching, right? Okay, sorry about that, guys. So to answer this question, it says, since the simulation shows few cases where there was a mean difference of negative 15.1 or less that occurred when the groups were re-randomized. So when you do these simulations, you take the sample data value up here. So you take these numbers and you randomly put them into groups and you calculate the mean and then you subtract them. So again, all of these numbers we put in a hat, like 51, 67, put in a hat, and you would just randomly pick them and put them in groups. That's called random assignment, okay? So because few cases happen like this, it can be inferred that the mean difference observed in this study was not very likely, was very unlikely due to the random assignment. So if it doesn't happen often, you cannot say it's due to the random assignment. So the results are significant, not inconclusive, significant. So few cases mean it's unlikely to happen by chance, by random, which means it is statistically significant. There is a difference between paper and non-paper. Good. And let's do one more of these, again, trying to find one that maybe is not statistically significant. All right, let's try this one. Again, there's all kinds of different problems in these. A school had a lot of problems with student absence and wanted to try an intervention program to see if it encouraged students to come to school more often. As a trial, 28 students were split into 2 equal-sized groups, so 14 and 14. Group 1, we get the new intervention. Group 2, we get no intervention. The mean number of absences are calculated after 1 month for each group as shown on the table. What inference can be made about the results? So again, this is the intervention group, and they got no intervention. So we're going to take our x bar 1 minus x bar 2. 2.5 minus 2.9 is a difference of negative 0.4. So we're probably going to go negative 0.4 or less because it's negative, right? If it was positive, we'd probably go more, depending on what the dot plot looked like or the histogram. So let's see how often that occurs in our 100 simulations. So 100 simulations. So we're looking for a negative zero point 0.4. So again, remember, negative 0.2, this is negative 0.4. It's included in this box here. So we're going to add up the frequency of these three boxes. So again, this is counting 0, 2, 4. So that bar has 3 in it. This bar has, that's 4, 6, 8. So this bar has 5, and this is 6, 8. So that bar has 7. So 3 plus 5 plus 7, that's 15 out of the 100 show a difference of negative 0.4 or less. That is a proportion of 0.15, which is less than which is greater than 0.05. Therefore, this can happen too often by chance to be significant. There is no difference if we randomly assign these numbers. There's no difference between the groups. Okay, so we'll come down here. So it says, since simulations show many cases where a mean difference of negative 0.4 or less occurred when we randomized, it can be inferred that the mean difference observed was very possibly due to the random assignment of groups. So again, it's not because it's significant, it's how the groups were randomized, right? So the results are inconclusive. There we go. Okay, so again, do your best on these. If you have questions, feel free to ask during the Google Meet, and best of luck. And again, this was just a introduction to statistics that you'll take further, possibly in your math career. And again, this was it. Congratulations, you made it. You will no longer hear my voice for a very long time. I hope you miss my voice, though. I really do. All right, see ya.